Hello everyone, this is Kai Guo from Samsung Electronics, South Korea. Now I'm present the paper, the robust Full-FoV data estimation in tele-wide camera system. It is accepted by ICASSP 2020. And as oral presentation, here we start. So our paper title is Robust Full-FoV data estimation in tele-wide camera system. Currently, the tele-wide camera system becomes very popular in current mobile devices. In mobile devices, in the back camera, it has at least one wide camera and also has at least one telescope camera. These two cameras have different field of view, FOV. So for this kind of asymmetric camera, to estimate the depth, use traditional stereo matching method. Matching cost calculation plus post processing is very difficult to get the full FOV depth like this. And there are some also some state-of-the-art single image depth estimation by the DEM method. It could estimate the full FOV depth here, but the quality is not good enough. And also now there is also the DEM-based tele-wide camera depth estimation method. The quality is also not good enough. The reason is, in my opinion, the pure DEM-based depth estimation method can obtain full FOV depth, but have low robustness for scenarios which are not covered by the training dataset. So to solve these problems, we propose a hierarchical hourglass network. It combines the robustness of traditional stereo matching method with the accuracy of the DEM. Here is the architecture of our proposed method. Here is the input of the color image. This is a white color image. And first module is single image depth estimation. It estimates an initial FOV depth. And the second is a depth propagation module. The traditional stereo matching based tele-FoV depth is here as the input. Then for the surrounding amplitude regions is filled by the initial FOV depth like this. Then it concatenates with the white color image as the input for the depth propagation. Then it will propagate the depth to the surrounding regions. And at last is the depth combination modules. The input is the depth propagation output here, concatenate with single image depth estimation here, and also the white color image as the input concatenated here. Totally, there will be 5 channels sent to a final depth combination module, then give our final output. All of these 3 modules use an hourglass model. It is a kind of encoder-decoder structure with skip connections. Here, our loss function is also a weighted combination of these 3 modules loss. Loss 1, loss 2, and loss 3. Here is to illustrate the effectiveness of each module. Figure A is the input white image, and the traditional stereo matching method output as shown here. Figure B is an intermediate result of a single image depth module. You can see that it could predict the global structure, but lack of details, especially for the uncommon objects like these photos, which are not covered by the training dataset. Figure C is an intermediate result of our depth propagation module. It would define the stereo depth at the tele-FoV region, at the same time propagate it to a surrounding region, but has slightly discontinuity artifact at the tele-FoV boundary. Figure D is our final depth output after depth combination module. It fuses the initial depth with the propagated depth to generate better results and smooth out the aforementioned discontinuity artifact. Here for the loss function here as aforementioned, we use the weighted sum of these 3 module loss functions. The weight W1, W2, and W3, we set them as 0.5, 0.5, and 1 respectively. So for the loss functions, L1, L2 and L3, we propose L1 norm scale invariant loss function which regulates predicted log depth to have similar between points relationships with ground truth. Compared with widely used L2 norm, L1 norm is robust and less sensitive to outliers. It's written by this formula. So it makes the between point relationship of predicted depth be similar with the between point relationship of the ground truth. Directly calculating this absolute difference of deviations on all possible pixels pairs is quite time consuming. To accelerate the calculation, we compute absolute difference of deviations only between each pixel and its neighboring pixels. Because of low correlation between a pixel and other spatial distant pixels of depth map, as shown here. This is a correlation between a single pixel and other pixels of depth map. We calculate this from the NYU depth V2 dataset. Then the L1 norm scale invariant loss function could be written as this form. Absolutely, the larger neighborhood could produce better results. Considering time complexity, we set neighborhood as a 17 by 17 window. This is an example to verify the effectiveness of L1 norm scale invariant loss function. Here, figure A is the input wide image. Figure B is our network with widely used L2 norm scale invariant loss function. Figure C is our network with the proposed L1 norm scale invariant loss function. You can see that our L1 norm scale invariant loss function could generate a better global structure, especially for the background. Then this is the example of results comparison on well-tested images. We capture several test images at various scenarios by tele-wide camera of Galaxy S9 Plus. Megadepth dataset is used as a training dataset. All of the images of training are skewed to 240 by 320, and the center region is used for the tele-FoV depth. And for the test, the tele-FoV stereo matching depth is obtained by the traditional stereo matching cost calculation and plus the post-processing. So here is the example comparison. Figure A and B is the input wide and tele image. Figure C is traditional stereo matching. Figure D and E shows two state-of-the-art DNN-based single image depth estimation output. Figure F is a state-of-the-art DNN-based tele-wide camera depth estimation output. You can see that this DEF has low quality for these two scenarios. And G, figure G is all proposed methods output. You can see that we have better global structure here, and also we have sharp boundary depths, and have is better quality, So this page to show our results comparison with state of the art on KT dataset. For the KT dataset, we use training images and test images based on the engine split. And to know the maximum benefit of a method, regardless of stereo depth quality, we use the center region of ground truth as tele-FoV depth for test. So because all of the training and test images are captured by the same device, we can combine the proposed L1 norm scale invariant loss function with the common L1 norm loss function to get the better result. Here is the comparison. Figure A is a wide image. Figure B is a state-of-the-art DNN-based single image depth output. Figure C is all output. Figure D is ground truth. We can see that we get better results in terms of the depth, sharpness, sharper edge, and the global structure. So this is objective comparison on the KT dataset. We use RMSE, IEL, and delta 1, delta 2, delta 3 matrix. RMSE is root mean squared error. IEL is mean absolute relative error. So delta 1, delta 2, delta 3 are percentage of predicted pixels where the relative error is within a threshold. You can see that for this RMSE and IEL, the lower value is better. So delta 1, 2, 3, the higher value is better. Our method is best compared with state-of-the-art DNN-based method. For the NYU dataset, we use a pixel split from the NYU depth V2 dataset, and all of the images of the MF map are scaled to 224 by 304. The central region is used as tele-FoV depth for training. Same with KT dataset to know the maximum benefit of our model regardless of stereo depth quality, and also the NYU depth has only single image without stereo pairs, so we use ground truth tele-FoV depth as input stereo depth. So because of the training and testing images of NYU dataset are captured by the same device, we can also use the combined loss function from the proposed L1 norm scale invariant loss and the common L1 norm loss. So this is result comparison. Figure A is reference wide input image. Figure B is a state of art single image DNA based depth estimation. Figure C is all results. Figure D is our ground truth. We can see that we can achieve much better quality in terms of global structure and sharpness. This is the objective comparison. Also use MSEIL, data 1, data 2, data 3. You can see that we achieve the best one compared with state of the art method. So here is as a conclusion. We introduced a hierarchical hourglass network for robust Full-FoV depth estimation in tele-wide camera system, which combines the robustness of traditional stereo matching method with the accuracy of DNA method. Experiment results demonstrate its robustness and better quality. We believe this method opens up a door for research on combining the robustness of traditional signal processing into deep learning for depth estimation in the future. We will investigate a new network structure and extend our framework into other computer vision problems. Thanks very much. Thanks very much to listen to my presentation. If you have any questions or problems, please contact me by email. This is Kaigo. Thank you very much.